All right, this midterm here, I'll get the scores up in Moodle here later on for those of you online. So that first one, you could have done it any number of ways. If you did it with vectors, you want to find the two radii, which are the vectors that go from the point that's the center point to the point that's rotating. So it'd be that line there, that's RB with respect to A. So you just use the length, use the angle of the linkage, which is 36, and get that broken into a vector. And then you do the same thing for the other one. You'll need it eventually. So the position of C with respect to B, you use the length and the 20-degree angle. The position from B to A is positive x minus y, and the position from B to C, excuse me, I might have misspoke. The position from A to B is positive x negative y, and the position from B to C is positive x positive y. Okay. Then what you do is you take cross products to get velocities. So the velocity of B is omega B crossed with R B with respect to A. So that'll be IJK, and then 006. It's positive 6 because that's a counterclockwise moment there, so that's a positive. You know, you do have to pay close attention to signs when you're doing this stuff. And then you put in the position vector, do the cross, and you get VB. 1.69I plus 2.33J. Okay, then you can do the same thing to get the velocity of C with respect to B, cross the unknown omega, which is just omega with the position vector. And when you do that, you'll get a negative 0.212 omega I plus 0.583 omega J. Okay. So now you've got the two velocities. You've got the velocity of B and the velocity of C with respect to B. You know that the velocity of C is in the J direction only. It has a 0I component. So you can put the relative motion equation together there and then solve out the I's first. Solve for omega, it's 7.97. And then do the J's, you'll get VC is 6.98. I was looking for an arrow on that to indicate the direction. Okay. Now, if you do that, doing it more geometrically, you might say, what you do, you use the angles that are 90 minus the linkage angles. So this velocity here is 90 minus 36, and that would be 54 up and to the right. So the magnitude of that is omega times the length, 6 times 0.48 is 2.88. Then you just go cosine 54 times 2.88I, sine 54 times 2.88J, so that's 1.69I plus 2.33J. Okay, then we've got the velocity of C with respect to B. That's perpendicular to this linkage. So that makes a 90-degree angle there. So 90 minus 20 is 70. So that's going up at 70 degrees up left. So like I got a little bit of a typo right there. This ought to be 0.62, is it? Yeah, 0.62. There we go. So that's 0.62 omega. So you're going to have a minus I and a positive j because that's up and to the left. So negative 0.62 omega cosine 70I plus 0.62 omega sine 70j. So that's negative 0.212 omega I plus 0.583 omega j. Okay. So then you can put that into the same vector equation we just looked at and solve it the same way. So you'll get omega is 7.97 and VC is 6.98. Yes. Oh. Okay. And then the last method, you could do it with that instantaneous center if you liked. You'd find the velocity of B, and what that is omega r, 6 times 0.48. Excuse me. Get that pollen's out a little bit there. So that's 2.88 meters per second for VB. And then once you've got that, what you would do is create that triangle for the instantaneous center. So what we've got this velocity going up that way, so that'll be 90 degrees. So that instantaneous center will run along this line that connects B to A. Then you also put in a perpendicular for the velocity of C, which is straight up. So that's kind of how you're building that triangle. So your instantaneous center is right there. Okay, that angle's 36. This angle's 20. This is what's left over, which is 124. So once you've got that, you can do the law of sines, do the ratios of the lengths to the sine of the opposite angle. Based on that, you can come up with BIC is 0.361 and CIC is 0.874. Okay. Once you've got that, you can take VB, which you know, 2.88, and divide it by its length. For the radius, 0.361, you get 7.98 radians per second, and then you can take that times the length from the IC to C. But you get 6.98 meters per second. That thing's going this way, so that will drive the velocity of C up. Okay, so that's the other way to do that. Any questions on any of that? So we're good? All right. Good to go? All right. All right, the next one is a work energy problem. You've got the things moving up and down, so you got that up arrow over here, so that's moving up. You've got the springs, so that's a tip-off if that's a work energy problem. What you want to do there is find the weight of the collar. It's 5.4 newtons. Then you want to find the length of the spring. So you got the 0.44 down there in both cases, and then you've got the other lengths that you'd be dealing with here too. So this one right there is 0.24, so that's where that comes from. And this other one here is 0.08, so that's where that comes from. So what you do there, you can do the theorem of Pythagoras and find the lengths of the springs. Okay. All right, so that gets you the length of the springs. Now you could do this in different ways. I tend to call the lowest point datum. Didn't have to do it this way, but that's how I do it. So that's going to give me a 0.32 meter height there times the weight, 5.4, so that's 1.73 for potential energy. Now if you called datum right here in the middle, which you could have done, this would have been 1.3 because it would have had a height of 0.24. And this would have been negative, which is important. That has to be a negative 0.43. In either case, the difference is 1.73, so so it's fine. Okay. Okay, then the spring energy, 1/2 K S. S is the amount of stretch in the spring. The unstretched length of spring is 0.28. Okay, so 0.501 minus 0.28 squared times 1/2 times the spring constant is 0.44, and 0.447 minus the 0.28 squared times 1/2 times 18 is 0.25. The collar is moving at position A. It's got a velocity of 2.1, so 1/2 mass times 2.1 squared is 1.21. Add everything up here, you get 3.38, I think. Anyway. No, I busted that. What do we got here? Hang on. I need a 2 out in front of that spring energy, which I didn't put in here. There we go. That's my bad. So what we end up with there is 3.82. Right there. That's what it should have been. Okay, then take away the work. Now the work is just given. The frictional force is 2.6 and the distance is 0.32. So the work is negative. It's negative 0.83. So this here is actually 0.88 on account of the 2 springs. There we go. Okay. And this is 0.5 because there's 2 springs. So if you take the 3.82, take away the 0.83, you get 2.99. This is 0.5 here, so the spring energy then is 2.3, I think it is. My key's a little bit messed up. 2.49, no, it's 2.49. There we go. Okay. So the leftover, so what we're doing here, we're taking the total energy, the 2.99, subtracting off the spring energy, which is 0.5, and that gets us to 2.49. Okay, so 1/2 times the mass times the unknown velocity is 2.49. So the velocity is 3.01 when you finish up. Okay. Any questions on that one? Doing all right? Yeah.
Where does the 0.32 come from?
0.3 in the work. That's the distance the collar travels, because it's going 0.24 down the shaft, and it's going another 0.08. So it's the 0.32 on the work is the sum of these 2 distances right here. That's how far down the shaft it goes. Right.
I thought last time that we used an average force, we didn't take into account the distance, because it was average or something like that. Might be misremembering.
Yeah, work is by definition force times distance. So you take the average force, in this case, times that total distance. Okay. Other questions? Okay. Okay. Okay, the next one there, you just need to do momentum. Now, if you do it in the X, it zeroes out. If I've got an arrow like that, generally I take that to mean in the Y direction only. But if you checked it out, the X momentum would zero out. So I just did the Y momentum here. So we're going to have 0.4 kilograms times 12 meters per second. There's no impulse because there's 2 objects that we're analyzing together. So the force of A on B is the negative of the force of B on A. So that zeroes out, and then that equals sine 18 times 0.34, which is the mass of A, times 5.047, then plus 0.04 times whatever VB is. VB2 over here is what we want. Okay, so you work that through. 0.48 is 0.530 plus 0.04 VB. VB comes out to be a negative 1.26. Now, when you do E, you've got to do it directionally, okay? So you've got VB2, which is 1.26, negative, and you got to put the signs in there too, so that's a negative. Then you'll have minus, because that's part of the formula, VA2, which is sine 18 times 5.047. Okay, and then VA1 in the y direction, which is how we're analyzing this, is 0. And then VB1 is 12. Okay, so when you plug all that in, you get 0.235. So the important things here is, I'm doing it in the y direction here is what I'm doing. And you got to remember the signs, a negative there. So any questions on that? All right. Okay, the one after is angular momentum. Okay, so what's going on with that is you have to do it angular momentum because the thing's spinning, it's rotating about that center point. And you treat it as two separate objects that are rotating, but they're rotating together. I mean, A and B are analyzed as separate terms, although they are linked by the fact that the angular velocity is equal for them. So that's the meaning of these summation signs here. You add up things together. Okay, so what you do first is you take D, which is 0.5, times the mass of A, 0.06, times its velocity, 1.5. And then take B, which is 0.04. Its mass is 0.075, and its velocity is 1.2. So that's the starting angular momentum. They're both positive because it's going counterclockwise, so that's the positive sign on that. Okay. Then you have this motor that inputs 0.027. Now I had a typo in here. I called that out in class, but somebody used the wrong moment. I just followed it through. If you did, it wasn't a big deal. I just followed it through. Okay, so that's plus 0.027 times 0.34 seconds. So that's the moment times the time. Then you've got the final terms. Now, you don't know what the velocities of either of those pieces are. They're rotating together, so you have to connect them by the fact the whole assembly has 1 omega. So what we're doing here, we're using V is equal to omega R. So for the second one here, we got 5 centimeters, which is 0.05 meters. The mass is 0.06, and the velocity would be 0.05 omega. Same thing for B. We got a 0.07 D, which is essentially a moment arm there. 0.075 for the mass and 0.07 omega. You could work it on through and find omega. It's 33.4 radians per second. And that gets you, when you multiply that back by 0.07 meters for the distance on that, you get the velocity. It's 2.34 meters per second. Now, had you used 0.27 for that moment, you should have come up with 13.5 would have been what you'd come up with. Okay. Good with that? Okay, the last one then. You use basic momentum to analyze it. Now what you've got the fact that the block comes to rest with respect to the cart. Now the cart and the block then are moving at the same velocity. So there's one velocity for the cart and the block. by the time it slides and stops. So you could just use straight momentum for the first part with the impulse going to 0, okay, because you're analyzing the system as the cart and the block together. So the mass of the block times its velocity is your starting momentum. The cart has no momentum because it has no velocity to start with. And then you equate that to the mass of both of them together times the unknown velocity, VBC. You can solve for VBC, and it's 0.142 meters per second. Okay. Now, what you can do next is you can look at the velocity and the acceleration. There's many ways to do this second part here. The acceleration would be 0.197 meters per second squared. That's just v equals v0 plus at. So you know the final velocity is 0.142 and the initial velocity was 0. So you can back into the acceleration of the cart, it's 0.197, and then plug that into this distance formula here. So you got s equals 0 plus 1/2 times the acceleration times the velocity squared, or excuse me, the time squared there. And that'll get you that distance. It's 0.0512 meters. Okay. Now you could have done the same thing for the block, and you would have come up with s as 0.699. But if you'd had that, you would have had to subtract off the 0.648 to get the distance, the 0.0512, because what we're after is just that distance there. We didn't want to include this distance in it. Okay. And you know, there's a myriad of ways to get that figured out. Okay. So any questions on that one? All right, so that's the second one there. Yeah, I know that people often have concerns, about grades and all that. I understand that. Keep in mind that I just have to focus on this one class and teach it and grade it in a fair way. So that's what I try and do. If you are thinking about where you stand in the class and all that, what I have here in Moodle is a grade calculator. It's in the downloads. So, if you're interested in that, you can pull this thing up. It's just a little spreadsheet is all it is. Remember, I use 2 different systems to calculate your grade. So you enter the scores on the top line. So homework, I'll get that back to you all on Friday. That's my plan. Normally, if you're doing your homework diligently, that should be up in the 90s. So let's say, 95 for that. And let's say you got a 62 on the midterm. Whoops. Oh, I got to make this so it'll edit, don't I? There we go. Okay, so you could put in, what you estimate your homework score to be. Keep in mind, I'll drop the lowest week of homework. Then you could put in your midterms. Let's say we got a 62 on the first one and a 64 on the next one, and we want to know what we got to do to, do decently in this class. I've got both methods here specified and the percentages assigned. Remember, there's 2 methods. So you could look and see what it would take to get a C out of the class. You can put in different grades, and looks like a 70 would do it. 69, that's probably about it. Maybe a 68. Yeah, 68 would get this person a C, okay? So that's just something you could play around with if you kind of want to know about where you stand, okay? Don't overdo that. I mean, you got to put the effort out on this final and all that. So don't be sure you're working hard, especially this stuff that'll be in the final is pretty challenging. So, okay. So that's available there to you if you like, okay? You could play around with it a little bit, see what it would take to get different grades. Okay. All right, so we good with that? We got any other questions on this stuff? Okay. I'll get you a review for the final here in a minute. Now, what we got coming up for the final is Wednesday from 3 to 5. If that's a real problem for you, I know a lot of you are OSU students here, you can talk to me about that. And, we could have a look, okay? But what we'll have on this thing is a few different topics. Okay, now the main things that we'll have on it will be the things that that we have covered since the last midterm. So a lot of this will be that rigid body kinetic stuff. So what that will include would be the translation, and then the rotation, and then the free plane motion. Okay, so that's the material that it would cover, okay? Why don't I see if I can't get you this stuff here. I'll just print it up right now. I'll go grab that. I'll just get a couple copies. Just while I'm thinking about it, I'll be right back.
This is like the slowest spot on the track, so it's not the best way to could have happened. That's as fast as they can get it. Say, then this is like left aisle, but it's a road course, like it's an island in the UK. They shut down for a week. the race, the streets would fall all the way on. Yeah, it's insane. It is like steep. This guy's like 60 something and he's still breaking the record. It's 20, 40 miles. I think it's 7 minutes. Yeah. Just wait till they're well, there is a couple of like actual race courses that have like a bump where they lock. Yeah. But yeah, they do here too. Yeah. Oh yeah. You get over that, or you have to pick up the phone and then they come down the hill. Yeah. They just go, man. 60 something, I think. There's some fast motherfuckers. There's a guy that used to come into the shop at Eugene. He's retired doctor, or mostly retired, and all of his money went into his track bike, and he just like, I think he maybe worked 1 to 3 days a month, and outside of that, he spent all the rest of his time at the track, just ripping. And he wasn't slow either, but like he never raced. He just went to the track to ride. Yeah, and then he doesn't have to worry about shit like this. Deer jumps out in front of you or whatever. Fastest lap I've ever been 32 months ago. Crazy. He missed this year because he broke his leg in the training. So last in that video was a sidecar wreck, the little one, the two video that came out, the second one, so Island. I thought it was he actually raced. It was just a promotion, but like at the end they gave him.
Okay, so these are available on Moodle too for those of you that are online. So let's have a look here. All right, so for starters here, the topics are going to be a lot of what you see there on on that sheet that I just gave you. All right, so what we've covered since the final is moment of inertia, so you should be ready to calculate those a bit. Then rigid body kinetics. And the three main topics are translation, fixed axis rotation, and general plane motion. Okay. So translation, what you're doing, generally two things. You're finding normal forces on wheels or supports, and you're finding accelerations before something tips. Okay, and the main thing you end up doing on that is right there, okay, that inertial moments equation. And tipping occurs when a normal force on one of the supports or wheels hits zero. Okay. Okay, fixed axis rotation is quite often involves finding alpha, which is the way you do that is right there. Either one of these equations can be used. Commonly it's this one, with A being the point about which the object rotates. And once you've got alpha, you can find the tangential acceleration. You might find the normal acceleration too if you have omega. And then you can find the reactions too. So that's another thing you can do with that. And then general plane motion, that one's a little bit more variable. Either you might go with a combination of some of F and some of mg as IG. It looks like I forgot an alpha in there, IG alpha. Or you can do this moments about point A equation, that inertial moments equation. You might need to use relative acceleration to find the acceleration of points other than G. With wheels, you might look at slipping and not slipping, drag and drive wheels, and find accelerations of a wheel. Okay. So those are the topics since the final since midterm 2 that could be on here. So if you look at some of those example problems which are pulled off of old tests, what you want to be able to do first is identify what kind of problem you've got, okay? So here we got a vehicle, we got a wind blowing on the vehicle. We want to find how much it can accelerate before it tips. So what is that? Is that translational or fixed axis rotation or free plane motion? That's translation, okay? How are you going to approach that? Okay, let's get this stuff, figured out by next week, frankly, okay? You want to identify this stuff and know how to do it, okay? What's going to happen here, these things tip in the opposite direction of the motion, of the acceleration, I guess I should say. And then what you're going to be looking at here is this normal being 0, okay? And then the equation you'll use will be sum of MA is I sub G alpha plus MAG XY bar plus MAG Y X bar, okay? That's how you do those. So, these things are challenging, I'm aware of that, but so to help you with that, I would really suggest you kind of first be able to identify these things and how to approach them, okay? Okay. So any questions on that one? I'm going to go at that. Okay. Okay, this one here, we got a person on a bicycle. We want to find the normal force on the front wheel at point A. What kind of problem is that? That's translation, right? Accelerating to the left, going to tip back, probably going to take moments about B. What do I do? Okay. That'll get you the reaction at A. Okay. Okay, this thing here, we're rotating about, let's see, assembly rotates about point A. At the instant shown, I give you the angular velocity. Find the X and Y reactions at pin A. Okay. That's a rotational problem, okay? So that's fixed axis rotation, okay? That's what that is. All right, so that one's got to involve because it has this weight hanging down here. What I did, I kind of used on this one's probably the trickiest of the bunch, is I used a summa MA equation there. And I kind of treated it like one of those pulley problems that we worked on. So I had sum of MA is equal to, and then I did the inertial moments stuff on that. So IG alpha plus MAG X Y bar plus MAG Y X bar, okay? So that's how I approached that one. So basically this is a rendition of that equation in a little bit different format because I did this a number of years ago, but that's basically what that is. And I did that because this weight here is joined to the plate by a rope. So it itself is not rotating. The plate rotates, but the block at B does not, okay? And also, this one is a little complicated because also I used I sub A to do the plate. So for the plate, the analysis I used on that was I sub A alpha right there. So that was kind of admittedly a tricky one, but that's, you could kind of go through that and figure out how that's approached, okay? Okay. Okay, this one here, we got a rod at a 27-degree angle rotating about A. So what I would do on this thing, this is fixed axis rotation. So I would go sum of MA equals IA alpha, and then I'd go sum of F X is equal to MAGX, and sum of Fy is equal to MAGY. That's how I would find those reactions, okay? You had a problem kind of similar to this in the homework that I think you turned in today. Okay, then I just have a disc rolling down a ramp. So that's a free plane motion problem there. And the way I approached this was just to go sum of Fx down the ramp is MAGX, and sum of MG is IG alpha. And then there's a few other things going on with this, but that's basically what I did. Could also have called that point A. You could also have gone sum moments about A. And again, done that whole drawn out equation there. Like so, okay? So could have done that as well. So you could either approach that with two equations or one. Okay, remember you assume no slipping on these things. That's generally the way you go into these, is you assume no slipping. And if you assume that, then you've got A is equal to alpha times R. Okay. And then we've also got, I think, a bit of a spool problem there, which we'll cover today a little bit on how to handle something like that. Okay. All right. So that's a good part of what will be on the final. Okay. Now there'll be some other things on the final as well. And those other things will be work energy and momentum. So have a look at your homework on that and that midterm you just got back. Okay. The question is, so there won't be anything from the first midterm. The answer to that is directly no, but a lot of that stuff is really integrated into what we're doing. So, what we're doing now is kind of an advanced version of the F equals MA stuff we did on the first midterm, really. So, yes and no, I guess, is the answer to that question. Okay. Okay, now, just to talk to you frankly about this stuff, this stuff isn't like statics. It's not, it's harder. I mean, I think some people find it easier, but I always found this a little harder. This is a fairly, it's fairly challenging, especially the stuff we've been going over lately. It's complex. It's got lots of details. So, when you're doing this and you're taking a test, I'm telling you, I'm going to give you one of those. Figure that stuff out. That's building a chart and filling in the chart and getting it. That there's a definite method to doing that. Identify work energy, fill in the chart, and do it. Momentum, a little less so, but there's certain specific things about momentum. You handle it as a vector. You look at, if you got two objects you're analyzing together, the impulse goes to zero, right? So if you could pick up easy points, do it, okay? I mean, just think about this stuff a little bit strategically, This stuff, of the three types of kinetics we're doing, this translation is pretty straight up. You apply that sum of moments equation to either find a reaction or see if something's tipping. That's not real, there's no curveballs in that, if you know what I mean. It's, I don't know, there's always harder things about things, but I can't just say that, but it's easier, I think, than the other stuff. So just be darn sure you can do those three things, that you can identify them and do them, okay? Because that's maybe 60% of the test right there, okay? I mean, get the stuff that's less hard. And just be sure you've got methods for those, that you can identify them and you know how to do them. Now, this stuff's a little harder. These last two topics, they're challenging. But I'm kind of lining out, standard things you do with these. Don't just learn to identify this and how you approach this general type of problem and do it. You can make some mistakes when you're doing it, take a few points off, but you'll probably do okay. But don't just try and make up your own method for doing this stuff, Identify it and apply the standard methods that are applied. And if you screw up on a couple of things, that's, it's okay, all right? Same thing with this stuff, There's certain standard problem types. We've had a lot of rolling objects here, that we analyze in a certain way. Do that. Even if you don't know every little detail of it, do that. Stay a little disciplined in how you approach it. It's my best advice on this. Okay? And you're gonna, you'll find out next year about hard engineering classes. I mean, frankly, that's, and I just want you to kind of think about that a little objectively too, Figure out how to approach these. Don't stay in the box, There's a certain way we do things, stay within that method and apply it. Make some mistakes within that application, but that's, that's okay. We all do that, okay? So I don't know, that's a little, I just want to speak with you frankly about this stuff. I took classes like fluid mechanics and thermodynamics and stuff. Stuff was difficult conceptually. It was Yeah, those are junior classes. Yeah, of course.
If we have twice as much time, should we expect twice as many problems?
No. You got 5 topics here. Looking like 5 problems. All right. Yeah, you know, it's so again, identify what it is and approach it the proper way. That's the message I'm trying to give you, you know. Because there's going to be 5 of them. You should know what a work energy problem looks like. You should know what a translational problem looks like and approach it the right way. You know? Okay. Okay, so this test is Wednesday at 3 to 5. I think the online version I'll have a Tuesday evening test from 6:30 to 8:30, I think is what I'm going to do for that. I'll send an email out on that. Okay. Okay. You want to, so any questions on this stuff so far? I mean, we'll take a break here and then we'll come back. We'll look at that homework that, you know, is due next week with the final. There's 4 problems yet, so we'll cover those next, okay? So if you got questions on things, you know, and you don't have them right now and they come up, you know, in the next 5 minutes or so, you know, just ask them when we come back, okay?